In this video, we're going to look at a type of infinite series called a telescoping series, because it's a nice special case that'll allow us to answer certain questions. So here's the two basic questions that we're going to ask about infinite series. We often want to know, if I have a series, does that series converge or diverge? And sometimes we don't even care to know what it converges to. We just want to know that it converges. Or I might also ask the question, if it does converge, what does it converge to? What's the sum of the series? Often we can answer this. Using a lot of the methods that we're going to study in the next few sections. We often can't answer this. At least not with the techniques that are taught in Calculus 2. But there are a few special series that we can find, whose sums we can find, so that we can answer the second question. Telescoping series are one of those. Telescoping series are a particular type of series whose partial sums only have a fixed number of terms after cancellation. Here's the general formula. I'm going to go back to this formula after we look at some specific examples. If you can write a series in this way, so let's say n starts at 1 and goes to infinity. If you've got a function evaluated at n plus a constant minus the same function evaluated at n, so it's the same function, except this one is evaluated at n plus a constant, and this one's evaluated at n, and we're subtracting them. That's generally the form of a telescoping series, and you'll see why in a second. So here's an example of a telescoping series. Notice that the form of 1 over n and the form of 1 over n plus 1 are very similar. I know these are in the reverse order from what you would expect from up there, but that's fine. You just need one of them to be positive, the other one to be negative, and one to be a function of n, and one to be a function of n plus a constant. And this is what we have. So let's expand this so that we can see what happens to the partial sums. So this is my a sub n. So a sub 1 has two parts to it. When I substitute in n equals 1, I get 1 over 1 minus 1 over 1 plus 1. So that's 1 minus 1 half. That's my a sub 1. And then I'm going to add what I get when I substitute in n equals 2. And then I'll add what I get when I substitute in n equals 3. And add what I get when I substitute in n equals 4. And so on. So this is my a sub 2. This is my a sub 3. And this is my a sub 4. And watch what happens. When I plug in n equals 2, I get 1 half minus 1 over 2 plus 1. So that's minus 1/3. When I substitute in n equals 3, I get 1 over 3 minus 1 over 3 plus 1, so 1 over 4. When I substitute n equals 4, I get 1 over 4 minus 1 over 5. And we keep going forever. Okay. I'll just rewrite these guys down here. Maybe I didn't need to write them twice. That's okay though. All right. So now look at these. Notice I've got a negative 1/2 and a 1/2. Those are gone. And a negative 1/3 and a 1/3. Those are gone. And a negative 1/4 and a 1/4. Those are gone. And then this negative 1/5 is going to cancel with a 1/5 from the next pair. So I think the sum of the series is just going to be 1. But we have to prove that. So in order to prove that, we need to find a formula for the nth partial sum. So this is telescoping because when I look at this, I've got a bunch of terms that cancel, and the nth partial sum is just going to have a finite number of terms. So it'll have 3 terms, 4 terms, sometimes just 2 terms. Now this is also telescoping. Notice I've got cosine of 1 over n and cosine of 1 over n plus 1. Let's see what happens when we substitute in n equals 1. we've got cosine of 1 minus cosine of 1/2. That's my a sub 1, because this is a sub n right here. That whole thing is a sub n. And then we'll substitute n equals 2. When n equals 2, I've got cosine of 1/2 minus cosine of 1/3. And notice that these reduce. Now, I mentioned earlier when I defined telescoping series, these are series whose partial sums only have a fixed number of terms. So just for this cosine one, let's look at the first three partial sums. S sub 1 is just a sub 1, so it's cosine of 1 minus cosine of 1/2. Obviously there's no cancellation there. We've got two terms. S sub 2 is a sub 1, so I'm just going to copy down exactly the same thing, plus a sub 2. That's the cosine of 1/2 minus cosine of 1/3. Third. And see what happens? These guys reduce, and my S sub 2 only has two terms. S sub 1 had two terms, S sub 2 has two terms. I bet you anything, S sub 3 is also going to have two terms. So I have cosine of 1 minus cosine of 1/2 plus cosine of 1/2 minus cosine of 1/3. So this is a sub 1, and this is a sub 2. And for S sub 3, we're adding the first three terms, so we need to add a sub 3. Well, when I substitute in n equals 3 here, I get cosine of 1 over 3 minus cosine of 1 over 4. Okay, and I've got a negative cosine of 1/2 and a positive cosine of 1/2, and a negative cosine of 1/3 and a positive cosine of 1/3. So I'm left with two terms. So I have two terms every time. So that's what makes this telescoping. The partial sums have a finite number of terms. And this is similar. It doesn't look like it's similar, but it is. And it's similar because of this property from algebra. If I have natural log of a over b, do you remember that there was a quotient rule for logs? That's log of the numerator minus log of the denominator. I hope you remember that. So even though this doesn't look like it's telescoping on the surface, it turns out that it is, because I can write that as log of the numerator minus log of the denominator. And now I've got a function of n plus 1 minus a function of n. So you see you've got one that's positive, one that's negative. The functions are almost exactly the same, but one is evaluated at n plus a constant, and the other one's evaluated at n. Here I've got n plus a constant and evaluated at n plus a constant and evaluated at n. So this is the general formula for a telescoping series. If your series looks like this, so it's a function, and basically the same function, but this one's evaluated at n plus a constant, and that one's evaluated at n. And you're subtracting them, well, then when you expand those summations, you're going to have a whole bunch of cancellations. And if you look at the partial sums, so like S sub n is the sum of the first n terms, a whole bunch of them are going to cancel except for a few at the end and maybe a few at the beginning. And so there's going to be a finite number of terms. And if you can find the formula for that S sub n, in general, because you've got a finite number of terms, you're just going to be able to write down that formula. We're going to do some pattern recognition, pattern matching to figure out what that formula is. If you can write down that formula, you just take the limit of the nth partial sum as n goes to infinity. That is the sum of this series. Okay, so that's what this section is about. This video is about. It's about telescoping series. They have this form, and this is. Let me outline what I just said. To determine if a telescoping series converges, we're going to do two things. You're going to find a formula for the nth partial sum. If it's telescoping, S sub n is something that we can find by looking at S sub 1, S sub 2, S sub 3, and then looking for the pattern. So we're finding S sub n through pattern recognition. And then you're going to compute the limit as n goes to infinity of s sub n. Now remember, the limit of the nth partial sum is the sum of the series. If I add all of these together and all of them cancel out, I think I'm just going to end up with this one right here, right? We need to prove it. So we'll find a formula for the nth partial sum and take the limit as n goes to infinity. If that limit is finite, then that's the sum of our series. I'm going to call this, compute this limit, which equals s, if s is finite. The original series, which we can denote by the sum as n goes from something to infinity of a sub n. Sometimes I'll leave off this number at the bottom and at the top. That's pretty standard, but if we need those, I will be very specific. This is usually like later in the problem. At the beginning, we really need to specify where we're starting and where we're ending up. If s is finite, the sum of the a sub n's is going to equal that s, because that's the definition of convergence of a series. If this limit exists and it's 5, this adds to 5. That's the sum of the series. If s is infinite, or if the limit does not exist, then the series diverges. The series that we started with diverges. Okay, so that's the plan. So for each telescoping series, we want to find s sub n, compute the limit as n goes to infinity of s sub n. If that is finite, that's the sum of the series. If not, we say the series diverges. Okay, so we said that one was telescoping, this is telescoping, this one is telescoping. We could go through and work all of those, but I've got other ones on the back of this that I'm going to work. So those were just examples of telescoping series, just so that you could see that the terms canceled. If you want to, you could work through those and see what the answers are. We're going to do some different examples instead. Okay, notice I've got a function of n and a function of n plus a constant. You might say, well, that's n plus a constant too. That's fine. The idea is that they have basically the same form. One has a positive sign, one has a negative sign, and they're off by like a couple of digits or two, or not digits, they're off by an integer or two, like n plus 1 and n plus 2 are only 1 unit apart. So if I expand this, and I always like to expand it just to get a better sense of what's going on. This is my a sub n. I want to find a sub 1 and a sub 2 and a sub 3, and we're going to add all of those together. A sub 1 comes from plugging in n equals 1 to this. 1 over 1 plus 1, that's 1/2. When n equals 1, I get 1/3 here. When n equals 2, I've got 1 over 2 plus 1, so that's positive 1/3. N is 2, I get negative 1/4. When n is 3, I get 1 over 3 plus 1 is 4, minus 1 over 3 plus 2 is 5, and so on. So that's our expanded series. I notice that it's telescoping because of this pattern at the beginning, or if I don't notice here, maybe when I expand it I see the negative 1/3 and the third reduce, the negative 1/4 and the fourth reduce, and so on. Now in order to determine whether this telescoping series converges or not, I'm going to find a pattern for the nth partial sum. So we're going to start by computing s sub 1, s sub 2, and s sub 3, and then looking for a pattern. So s sub 1 is just the first term. And I know the first term looks like it's got 2 terms in it. We're just treating the term as this expression here. That's a sub n. So a sub 1 is this 1/2 minus 1/3. No cancellations yet. S sub 2 is the sum of the first 2 terms. So that's this guy plus this guy. And I'm going to add parentheses just for emphasis to say that's a sub 1. And now I'm adding a sub 2 over here. and I notice that the 1/3's reduced. So we're just left with 2 terms. And then we'll compute S sub 3. And then we look for cancellations. The negative 1/3 and the 1/3 reduce. The negative 1/4 and the 1/4 reduce. And this is the process that you'll follow generally. Compute S sub 1, S sub 2, S sub 3. And then you're looking for a pattern. You want to find the formula for S sub n. Okay. Now with this, I always try to look for, 2 things. First, I look for what's staying the same as I go from term to term. And then I look for what's changing. And then I try to relate the change that I see to the index over here. Because the changed part on this side should be a function of n. It should depend on which partial sum we're talking about. Okay, so let's first identify what's staying the same as we go from term to term. Or from partial sum to partial sum. So this has a 1/2 in it, this has a 1/2, and this has a 1/2. So looks like that 1/2 is never going to reduce. There's never anything that's going to cancel with that. So what's staying the same is the 1/2s. So the first thing I can write down for S sub n is a 1/2. And then I notice what's changing. I've got a negative 1/3, a negative 1/4, and a negative 1/5. Well, they all have a negative 1 in them, but those denominators are changing. So let's focus on what's changing. There's a 3 that changes to a 4 and the 4 that changes to a 5. And then let's focus on the relationship between those numbers and the index of that nth partial sum. So I notice when this is a 1, that's a 3. And 1 plus 2 is 3. Okay. When that's a 2, that's a 4. Well, 2 plus 2 is 4. When that's a 3, that's a 5. 3 plus 2 is 5. So I think this is always 2 more than that. Is 1 plus 2 more is equal to 3. 2 plus 2 more is equal to 4. 3 plus 2 more is equal to 5. So n plus 2 more is going to be an n plus 2. So that's my formula. Now once you've found the formula for the nth partial sum, it has a finite number of terms, it only has 2 terms. Now you're going to compute the limit as n goes to infinity of that nth partial sum. If that exists, that's the sum of your series. All of these guys add together to give you the sum of the series, which is the limit of this as n goes to infinity, provided that limit exists. So we're going to compute the limit of this now. As n goes to infinity, 1 over a really large number is a really small number, so that's gone. And we get a finite number, 1/2. So now we're going to interpret that as the sum of this series. So that's our capital S. So our conclusion is the series that we started with, the sum as n goes from 1 to infinity of 1 over n plus 1 minus 1 over n plus 2. That equals 1/2. Infinitely many terms, you add them together, you get 1/2. So we computed that limit since it was finite. We interpret our result either as a sum of the series, or we say that the series diverges if the limit does not exist. So I can write the series, the sum of the series is 2, or I can say the series converges to 2, or excuse me, I said the sum of the series is 2. The sum of the series is 1/2, or I can say the series converges to 1/2. Okay, so that's that example. Now let's look at another example. Now this one on the surface does not look like it's a telescoping series, but I can use partial fraction decomposition to rewrite that. So I'm going to use partial fractions. I think we all probably need a little bit of a partial fractions review. It's been a while, and it's a very important skill that you'll be using again in differential equations. So I see I've got a constant over a linear factor times a linear factor. According to the method for partial fraction decomposition, this will have to equal some constant over the first factor plus some constant over the second linear factor for some unknown constants a and b. To figure out what a and b are, after I've written down the form of the partial fraction decomposition, we need to multiply by the LCD. Now, actually, let's go back to this series. We notice we have this. It doesn't look like it's telescoping, but it is telescoping. So we have decided to use partial fraction decomposition to write a sub n as the sum or difference, hopefully difference so that it's telescoping, of two terms. And part of the reason why I put this example in the video is because I wanted you to review this. It's such an important concept as you go on to differential equations. Okay, so I've got a linear factor, I get a constant over that factor. Another linear factor, I get a constant over that factor. I add those together and I get this for some values of a and b. To find a and b, we multiply both sides by the LCD. So we state the correct form of the partial fraction decomposition, and now we multiply by the LCD. So we've got n times n plus 2 over here, n times n plus 2 over here, and n times n plus 2. All right, now by design, when you multiply by the LCD, those denominators should reduce. The n's reduce and the n plus 1's reduce. That's good. I shouldn't have any fractions when I'm done multiplying by an LCD. I get a 4. The n's reduce here, so I have a times the quantity n plus 2. And the n plus 2's reduce here, so I've got b times the expression n. So I've multiplied by the LCD. Since I had two linear factors, neither one repeated, I will choose values of n that make each of the values, or each of the factors, 0. And then when I do that, I plug those values of n into this equation, and that allows me to solve for a and b. So we will choose values of n that make n plus 2 equal to 0 and n equal to 0. Well, n equals 0 is the easy one, so let's do that first. Nothing to solve there. When n is 0, we have 4 equals a times 0 plus 2 plus b times 0. You might not even write all of that down. You might do all that arithmetic in your head, but I just wanted to show you. I was literally replacing the n with a 0. So now I've got 4 equals 2a. So divide both sides by 2, and we get a equals 2. Okay, cool. Now, n plus 2 is 0 when n is equal to negative 2. That's what would make this disappear. So I have 4 equals a times negative 2 plus 2 plus b times negative 2. That's 0 by design. So we have 4 equals negative 2b. Divide by negative 2 on both sides to get b by itself. So b equals negative 2. So we chose the values of n that make each of the factors equal to 0. Substitute those into the equation. And then you end up with two equations. You solve those for a and b. Okay, so we got a is 2 and b is negative 2. So now, my original sum was a sum of 4 over the product n times n plus 2, it can be written this way. This is the sum as n goes from 1 to infinity of a over n, a is 2, so that's 2 over n, plus b, which is negative 2, over n plus 2. Ah, that looks like it's telescoping, isn't it? They have exactly the same form. One's positive, one's negative, one has an n, one has an n plus 2, so this is going to work just fine. So we're going to start there on the next page, and we're going to find the nth partial sum of our series. All right. Oops, 1 to infinity, sorry. Now, if you want, you can expand this to start. You don't have to. But I think it helps me. Maybe it just primes my brain. Reminds me what it is I'm actually doing. Okay. So there's my series. And here's a sub 1, here's a sub 2, here's a sub 3, and we're going to add all those together. And this is a sub n. When n equals 1, we get 2 over 1, and n is 1 here, so I've got 2/3. When n equals 2, we get 2 over 2. And if n is 2 here, I get 2 over 4. When n is 3, I have 2 over 3. And 3 plus 2 is 5, so 2 over 5. Okay, so that is what our series looks like expanded. And now I want to try to find a pattern for the nth partial sum. So we are going to follow this process again. We're going to compute s sub 1, s sub 2, s sub 3, and look for a pattern. We're trying to find s sub n. So s sub 1 is just this first term. It's 2 minus 2/3. No cancellations yet. That was just our a sub 1. And s sub 2 is a sub 1 plus a sub 2. So that's 2 minus 2/3 plus 2 over 2 is 1 minus 1/2. Ooh, no cancellations yet. Might make me worry. S sub 3 is a sub 1 plus a sub 2 plus a sub 3. So I'm going to copy down everything that I had from before. Oops, plus. We're adding those, not multiplying, sorry. A sub 3 has the 2/3 and the 2/5. Do I have any cancellations now? Oh, that's good. That's a good sign. I'm starting to see some terms cancel. All right. Let's look at s sub 4. A sub 1 plus a sub 2 plus a sub 3 plus a sub 4. Now I know I said just do s sub 1, s sub 2, and s sub 3, but I'm going to go out as far as I need to in order to see the pattern. I only had one cancellation. I want to see more cancellations, so I'm going to keep going until the pattern is obvious to me. If you already know what the pattern is, you don't have to keep going. You can stop. But if it's not obvious to you yet, I would make sure you do it. Keep going until you see the pattern. So here's A1, here's A sub 2, here's A sub 3, and here's A sub 4. To get A sub 4, I'm replacing the n's with 4's over here. So I get 2 over 4, that's 1/2, minus, if n is 4, I get 2 over 6. 2 over 6 is 1/3. Ooh, I had a negative 2/3 and a positive 2/3. I had a negative 1/2 and a positive 1/2. I have this random 1/3 here. I had 2 terms at the beginning, then I had 4, then I had 1, 2, 3, 4 that didn't cancel. Now I've got 1, 2, 3, 4 that don't cancel. Okay. I'm going to try one more. I know it might seem like overkill. I will be more comfortable if I can see that pattern. So here is a sub 1, a sub 2, a sub 3, a sub 4, and the last one is a sub 5. I'm plugging in n equals 5 to a sub n up here. So when n is 5, I get 2/5 minus 2 over 5 plus 2 is 7, so 2 over 7. Now look for anything that reduces, any terms that cancel. The negative 2/3 and the positive 2/3 still cancel. The negative 1/2 and the 1/2. Hey, I've got negative 2/5 and 2/5. And the negative 1/3 and the 2 over 7 are still there. Okay. So I think I am starting to see a pattern. I've got 1, 2, 3, 4 digits, or four terms, or what would traditionally be called a term left. Now let's look at what's staying the same as you go from term to term. Well, I notice all of them have a 2 in them. So they start with a 2. Every single one of these guys has a 2 in it. Okay. So I can write that down. Now S sub 1 is a little different. It doesn't follow exactly the same pattern because it only has 2 pieces. But all the others have 4 left. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. They all have four little terms remaining. So I'm still going through all of these. Let's just ignore S sub 1 for a minute and then look for a pattern. Do S sub 2, S sub 3, and S sub 4 and S sub 5 have anything else in common? I think they all have the 1. So there's a 1 here, and a 1 here, and a 1 here, and a 1 here. So they all have the 2 plus the 1. Okay. Anything else in common? I've got negative 2/3, negative 2/3 and negative 1/2, negative 1/2 and negative 2 over 5, negative 2 over 5 and 1/3, negative 1/3 and 2 over 7. Oh gosh, I don't see anything in common. Okay, so we're done with the 2 parts that they have in common. The other parts change. And this is tricky. This is a little tricky. So I need to think about what's the formula for the parts that are changing? And how is that related to these subscripts over here? Well, let's see. Let's focus on, let's sort of quarantine this guy. Got coronavirus on the brain now because I had a conversation with a friend about it recently. I'm going to quarantine that guy and just focus on the rest of these over here. So I have this quarantine language in my head, sorry. All right, let's see if we can't find a pattern for, let's say, not the last one, because the 1/2, the 2/5, the 1/3, and the 2/7. Let's try to find a pattern for the second to last one. So we've got a negative 2/3, positive 1/2, negative 2/5, and a positive 1/3. It doesn't seem that there's a pattern, but I think there must be a pattern, right? So this is a 2 over 3, and we're subtracting all of these guys. So I can put a minus sign there. That's good. Got something. And I want to look at the relationship between the 2 and the 2/3. Okay, I don't really see one. I mean, the numerators are the same. The denominator is the 2 plus the 1. And then over here I've got a 1/2. Ooh, how is that related to that 3? And this 4 and the 2/5. Ooh, goodness. And the 5 and the 1/3. Oh, it doesn't seem like there's a pattern at all. But there is a pattern. There has to be a pattern. Okay, so now let's think back. Where did these numbers come from? How did I get this 2 over 3? Well, it came from substituting in a particular value of n right here. For a sub 1 on s sub 2, I plugged in n equals 1. So I had a 2 over 1 plus 2. That gave me that 2/3. All of these should have a 2 in the numerator. The ones that don't, I think I must have simplified those. So let me change them so that they all have that 2 in the numerator. I think that was a 2 over 4 before simplification, and that must have been a 2 over 6. So now they all have 2's in the numerator. That's going to make it a little easier. Okay, so now let's think about the relationship between this denominator and this number. That's a 2 and that's a 3. If I change that to a 2, that's a 3 and that's a 4. Oh, that's encouraging. That's a 4 and that's a 5, and that's a 5 and that's a 6. Aha! Now, so I guess that's a good sign to you. You don't want to simplify these fractions as you go through. Now I can see the pattern. There's a 2 and 1 more than that, a 3 and a 1 more than that, and a 4 and 1 more than that, and a 5 and 1 more than that. So if this is an n, this has got to be 1 more than n. So that's got to be an n plus 1. Okay. Woo! Similarly, the last one, I think we're going to have to do the same thing with those guys. It's hard to find those patterns when you simplify. I shouldn't have simplified. When I substitute in n equals 2 to this, I got 2 over 4. So I'm going to rewrite this guy as 2 over 4. And when I substitute n equals 3 into this, I got 2 over 5, so that's good. N equals 4 into this, I got 2 over 6. So I should call that 2 over 6. N equals 5 into that, I get 2 over 7. So don't simplify. It'll help you recognize the pattern. Now let's look at the last term. So I've got 2 over 4, 2 over 5, 2 over 6, and 2 over 7. Now that is a pattern that I can wrap my head around. They all have 2's in the numerator. And now let's look at the relationship between the denominator and the subscript over here, the index of the summation. For the second partial sum, when that's a 2, that's a 4. When that's a 3, that's a 5. When that's a 4, that's a 6. So I think these numbers are all just 2 more than that. 2 plus 2 is 4. 3 plus 2 is 5. 4 plus 2 is 6. 5 plus 2 should be 7. And is it 7? It sure is. So it worked out. If this is an n plus 2 should be right there. All right, guys, we found the pattern. And here is a big note for your notebook. Don't simplify the fractions as you go. If you simplify, it'll be harder to recognize the pattern. Okay, so we've got this as our nth partial sum. And now if I want to determine the sum of this series, I take the limit as n goes to infinity of the nth partial sum. If that limit exists, the series converges. If the limit does not exist, the series diverges. So we're computing the limit as n goes to infinity of s sub n, which is the limit as n goes to infinity of 2 plus 1 minus 2 over n plus 1 minus 2 over n plus 2. As n goes to infinity, 2 over something really large is something really small, so that's going to 0. 2 over something very large is really small, so that goes to 0, and I just get a 3. So what does that mean? Remember, the limit of the nth partial sum is the sum of the series. So this is telling us that the series which was originally this series before we did partial fractions, when you add all of these guys up as n goes from 1 to infinity, you get 3. So the series converges to 3. I think that's pretty cool. So remember, you're looking for the pattern for the nth partial sum. Don't simplify, it'll make it easier to find the pattern. Find the pattern, compute its limit as n goes to infinity, the limit of the nth partial sum, and then if that limit exists, interpret your result in terms of the series. And this time, since the limit exists, we are interpreting the result as the sum of the series. And we can say that the series converges to its sum. Okay. So I think that's probably good for examples of partial fraction or of telescoping series. We did get pretty far with this one, so I think I want to finish this one. When we wrote out the first partial sum here, which is cosine of 1 minus cosine of 1/2, here we had cosine of 1, this is a sub 1 plus a sub 2. We had cosine of 1 minus cosine of 1/2 plus cosine of 1/2 minus cosine of 1/3. So the second partial sum was this plus this, and those two reduced and we got this. The third partial sum was this. These guys all reduced. If I want to find the formula for S sub n, I look at all of these guys and I think about what they have in common. They all have this cosine of 1 in common. Now you might be tempted to say that that simplifies, but it doesn't. Cosine and sine simplify when what's inside is a multiple of pi over 2 or pi over 4. If you just have an integer in there, like 1, it's a nice number. It's some number between -1 and 1. But it doesn't simplify with a nice answer like the multiples of pi do or fractions of pi do inside our trig functions. So S sub n has a cosine of 1 in it, which is just some number between -1 and 1. We could use our calculator to figure out what it is, get a decimal approximation at least. And then we're subtracting cosine of something. I've got a cosine of 1/2 here, a 1/3 here, and a 1/4 here. So I'm looking for a pattern. I'm looking for a relationship between this 1/2 and that subscript of a 1. The denominator's 2 when that's a 1. The denominator's 3 when that's a 2. The denominator's 4 when that's a 3. So when this is an n, I think this has to be 1 more than that. It has to be n plus 1. Now that we have the nth partial sum, we can take its limit as n goes to infinity, provided that limit exists. And cosine, or as n goes to infinity, 1 over n plus 1 approaches 0, so this is cosine of 0, but cosine of 0 is actually equal to 1. So that's for the other problem, that logarithm stuff. So we're going to have cosine of 1 minus 1. That's the sum of this series. Out of all of these guys, you're going to get something that's very, very close. Well, if you add up all of them, infinitely many of them, you're going to get cosine of 1 minus 1. As you take partial sums, if you add up the first 100 terms, you're going to get something very close to this. Out of the first 1,000 terms, you're going to get something very close to this as well. As you take more terms, generally, you're going to get closer and closer to that. Okay, so those are our telescoping series, guys. Again, remember, the way you recognize them is they can be written this way. They are a function of n plus a constant minus a function of n, or those could be reversed. It's basically a function, two functions with the same form. One's positive, one's negative, and one involves an n plus a constant and the other one involves an n. If I see something that looks like that, I know it's telescoping, and I can find the sum of the series or determine if the series converges or diverges by finding S sub n and then computing its limit. So go through this video, make sure that you're comfortable with these. You're going to see some others. Now, some of the telescoping series, like those we've seen on this video, are very obvious, like that. They have the same form, there's a minus sign. These guys have the same form and there's a minus sign. Some are a little less obvious, like that. Doesn't look telescoping, but if I use this property from algebra, I can see that it is telescoping. Now this one was obviously telescoping, but this one doesn't look telescoping, but it turns out if you use partial fraction decomposition, it is telescoping. It looks like that. So sometimes you might have to use partial fractions or log properties in order to show that the expression is or the nth term has the right form so that the series is telescoping. And then again, you're going to follow this procedure. Compute the first few terms and look for a pattern. Find a formula for that pattern. Compute the limit as n goes to infinity of the nth partial sum. If that limit exists, the series converges to that number. We add up all these terms and we get something we get exactly 3. If we add some partial sum, maybe the first 1,000 terms, we're going to get something close to 3. If we could add all of them together, we would get 3. So those are our telescoping series.